Good morning. Today we will study about the defects in solid. Stoichiometric and non-stoichiometric defects in crystals. At absolute zero, crystals tend to have a perfectly ordered arrangement. As the temperature increases, the amount of thermal vibrations of ions in their lattice sites increase, and if the vibrations of particular ions becomes large enough, it may jump out of its lattice site, and this constitutes a point defect. Higher the temperature, the greater the chance that lattice sites may be unoccupied. Since the number of defects depends on the temperature, they are sometimes called thermodynamic defects. The defect which arise due to the irregularity in the arrangement of atoms or ions are called atomic imperfections. If the deviations from periodicity extend over microscopic regions of the crystals, they are called lattice defects. And the lattice defects may extend along lines. These are known as line defects, or along planes, which are known as plane defects. And now the stoichiometric defects. Stoichiometric compounds are those where the number of different ions of atoms or ions present are exactly in the ratios indicated by their chemical formula. They obey the law of constant compositions, that the same chemical compound always contain the same elements in the same composition by weight. Two types of defects may be observed in stoichiometric compounds. These are called Schottky and Frankel defects. Schottky defects. A Schottky defect consists of a pair of holes in the crystal lattice. One positive ion and one negative ion are absent, as shown in the figure. This sort of defect occurs mainly in highly ionic compounds where the positive and negative ions are of a similar size, and hence the coordination number is high, usually 8 or 6. For example, in NaCl, cesium chloride, potassium bromide, and this defect decreases the density of the crystal. Second is Frankel defect. A Frankel defect consists of a vacant lattice site, that is a hole, and the ion which ideally should have occupied the site now occupies an interstitial position. Metal ions are generally smaller than the anions, thus it is easier to squeeze cation into alternate interstitial positions, and consequently it is more common to find the positive ions occupying interstitial positions, and this type of defect is favored by a large difference in size between the positive and the negative ions, and the coordination number is usually low, that is 4 or 6. Since small positive ions are highly polarizing and large negative small positive ions are highly polarizing and large negative ions are usually polarized. These compounds have some covalent character. This distortion of ions and the proximity of like charges leads to a high dielectric constant. And example of Frankel defects are zinc sulfide, silver chloride, silver bromide, and silver iodide. And there is no change in the density of the crystals due to this defect. Now, what are the non-stoichiometric defects? Non-stoichiometric compound exists over a range of chemical composition. The ratio of number of atoms of one kind to the number of atoms of the other kind does not correspond exactly to the ideal whole number ratio implied by the formula. Such compounds do not obey the law of constant composition, and there are many examples of these compounds, particularly in the oxides and sulfides of the transition elements. For example, FeO exists as non-stoichiometric compounds having composition Fe0.91O to Fe0.95O. Similarly, in vanadium oxide VOX, X varies from 0.6 to 1.3. In these compounds, electrical neutrality is maintained either by having extra electrons in the structure or changing the charge on some of the metal ions. This makes the structure irregular in some ways, that is, it contains defects, which are in addition to the normal thermodynamic defects. The defects which disturb the stoichiometry of the compound are called non-stoichiometric defects, and these defects are either due to the presence of excess metal ions or deficiency of metal ions. First type are metal excess defect due to interstitial. Metal excess defects due to anion vacancies. In this defect, a negative ion may be absent from its lattice site, leaving a hole which is occupied by an electron, thereby maintaining the electrical balance. This is rather similar to a Schottky defect, in that there are holes and not interstitial ions, but only one hole is formed rather than a pair. And this type of defect is formed by crystals which would be expected to form Schottky defects. When compounds such as NaCl, KCl, lithium hydride, etc. are heated with excess of their constituent metal vapors or treated with high energy radiations, they become deficient in the negative ions, and their formula may be represented by AX1 minus delta, where delta is a fraction. The non-stoichiometric form of NaCl is yellow, and the non-stoichiometric form of KCl is violet in color. The similarity with the flame coloration for sodium and potassium. The crystal lattice has vacant anion sites which are occupied by electrons. Anion sites occupied by electrons in this way are called F centers, because F is an abbreviation for Farbe, the German word for color. These F centers are associated with the color of the compound, and the more F centers present, the greater the intensity of the color. The solids containing F centers are paramagnetic because the electron occupying the vacant sites are unpaired. When material with F centers are irradiated with the light, they become photoconductors. When electrons in the F centers absorb sufficient light or heat energy, the electron is promoted into a conduction band, rather similar to the conduction bands present in metals. Since conduction is by the electron, it is n-type semiconductors. Second type is metal excess defects due to interstitial cations. Metal excess defect may also occur when cation occupies an interstitial positions in the lattice, and electrical neutrality is maintained by the incursions of an interstitial electrons, as shown in the figure. Their composition may be the general formula 1 plus delta X. And this type of defect is rather like a Frankel defect, in that anions occupy interstitial positions, but there are no holes and there are also interstitial electrons. And this type of metal excess defect is much more common than the first and is formed in crystals which would be expected to form Frankel defects. That is, ions are appreciably different in size, have a low coordination number, and have some covalent character. And examples are zinc oxide, cadmium oxide, Fe2O3, Cr2O3. When defected oxide is heated in dioxygen and then cooled to room temperature, its conductivity decreases. This is because the dioxygen oxidizes some of the interstitial ions, and these remove interstitial electrons, which decreases the conductivity. Crystals with either type of the metal excess defects contain free electrons, and if these migrate, they conduct an electric current. Since there are only a small number of defects, there are only a few free electrons that can conduct electricity. Thus, the amount of current carried is very small compared with that in the metals, fused salt or salt in aqueous solutions. And these defected materials act as semiconductors. Since the mechanism is normal, electrons may be excited to higher energy levels, giving absorption spectra, and in consequence, their compounds are often colored. That is, non-stoichiometric NaCl is yellow, non-stoichiometric KCl is violet, and zinc oxide is white when cold but yellow when hot. The yellow color of zinc oxide is due to trapped electrons. And then C, that is metal deficiency due to missing cations. The defect arises when a positive ion is absent from its lattice site. The charges can be balanced by an adjacent metal ions having an extra positive charge, and example of these are FeO, NiO, Fes, and CuI. If an Fe2 plus is missing from its lattice site in FeO, then there must be two Fe3 plus ions somewhere in the lattice to balance the electrical charges. Similarly, if a nickel 2 plus ion is missing from its lattice site in NiO, there must be two Ni3 plus present in the lattice. Crystals with metal deficiency defects are semiconductors. Suppose the lattice contains A plus and A2 plus metal ions. If an electron hops from an A plus ion to the positive center and A2 plus ion, the original A plus becomes a new positive center. There has been an apparent movement of A2 plus ion with a series of similar hops. An electron may be transferred in one direction across the center. And at the same time, the positive hole migrate in the opposite direction across the structure, and this is called positive hole or a p-type semiconductor. If a defect oxide of this type is heated in dioxygen, its room temperature conductivity increases because the dioxygen oxidizes some of the metal ions, and this increases the number of positive centers. Then D is metal deficiency due to interstitial anions. Theoretically, it is possible to have an extra anion in an interstitial position and to balance the charges by means of an extra charge on an adjacent metal ion. However, since negative ions are usually large, it would be difficult to fit them into an interstitial positions. No examples of crystal containing such negative interstitial ions are known at present. Then extrinsic point defects are defects introduced into a solid as a result of doping with an impurity atom. Extrinsic defects, those resulting from the presence of impurities, are inevitable because perfect purity is unattainable in practice in crystals of any significant size. And such behavior is commonly seen in naturally occurring minerals. Thus, the incorporations of low levels of chromium into the aluminum oxide structure produces the gemstone ruby, whereas replacement of some aluminum by iron and titanium result in the blue gemstone spire. The dopant species normally has a similar atomic or ionic radius to the species which it replaces. Thus, chromium in ruby and iron 3+ in spire have similar ionic radii to aluminum 3+. Impurities can also be introduced intentionally by doping one material with another. An example is the introduction of arsenic into silicon to modify the later semiconducting properties. Then what are n-type semiconductor? When group 14 elements like silicon or germanium is doped with a group 15 element like phosphorus or arsenic, then 4 out of 5 electrons of phosphorus or arsenic are used in the formation of 4 covalent bonds with the 4 neighboring silicon atoms. The 5th electron is extra and becomes delocalized. This delocalized electron increases the conductivity of doped silicon or germanium. Here the increase in the conductivity of silicon or germanium is due to negatively charged electron. Hence silicon or germanium doped with phosphorus or arsenic is called n-type semiconductors. Then p-type semiconductors, when group 14 elements like silicon or germanium is doped with a group 13 element like boron or aluminum, then the place where 4th electron is missing is called electron hole or electron vacancy. An electron from a neighboring atom can come and fill the electron hole, but then a hole is left in the neighboring atom. If it happens, it would appear as if the electron hole has moved in the direction opposite to that of the electron that filled it. Under the influence of electric field, electrons would move towards the positively charged plate through electronic holes, but it would appear as if the electron holes are positively charged and are moving towards negatively charged plate. And these type of semiconductors, they are known as p-type semiconductors. And doped semiconductors are essential components in the modern solid-state electronic devices found in radios, television sets, pockets, calculator and computers. And devices such as transistors which control electrical signals in these products are made from n-type and p-type semiconductors. If we have a crystal in which one part acts as p-type and the other as n-type, then the p-n junction will only allow the current to flow in one direction. And this type of p-n junction is used in rectifiers and used for converting AC into DC. Thank you. Have a nice day.